Hello everyone, myself is Rahangdale. This is my Altair simulation challenge entry. So I'll be simulating a landing gear of a B-1 bomber aircraft. Firstly, the cab, we have a frame here which will be acting as the ground. Then we have the actuator, it is a pneumatic actuator. And then we have the final bracket which is attached to the frame, and at the lower end it is attached to the three links. There are four links in this linkage mechanism which is responsible for the lowering and the lifting of the landing gear. Then we have the upper strut and the piston rod, which will be acting as the damping mechanism. In the simulation, we have not simulated the damping mechanism, as the goal is to simulate only the lifting and the lowering of the landing gear. Then we have the clevis, which is attached to the axle, and at the upper end, it is attached to the piston rod. Then we have the upper TA and the lower TA, which are responsible for the motion of the wheel assembly, and it is also attached to the axle. So this was a brief description of the CAD. Then we'll be defining the motion of the landing gear. Then here we have the ground, which will be acting as stationary. Then we have the rigid groups. They will be not moving relatively to each other. So we have defined four rigid groups. The first one is the upper strut rigids, which are the upper strut, the piston rod, and the clevis. Then we have the wheel axle rigids, which is the wheel and the axles. Then we have the link 1 rigid, which are the two parts of the link, and the link 3 rigid, which is again the two parts of the link. So this was the rigid groups. Then we will be defining the joints. So in Spire, automatically detects all the joints via the cavities and the holes in the CAD. So firstly, here we have the pin joints, uh, which are the hollow cylinder which go through the entire region. Firstly, we have the clevis and the axle connected via pin joint and given a motor for the actuation. Then we have the again pin joint between the lower TA and the axle. Then we have a cylindrically lock joint between the interlink and the lower TA. Then between the upper TA and the lower TA, we have a small socket joint and a pin joint to allow the movement in all directions. Then we have the pin joint here between the upper strut and the upper TA. Then the locking link and the link 3 is attached via pin joint to the upper strut. Similarly, the link 2 is attached via hinge joint to the upper strut. Then we have the link 1, which is attached to the frame and at the upper end, and attached to the upper strut at the lower end of the link. Then here we have defined a cylindrical joint in the actuator to simulate the actuator. Then we have the pin joint at the bracket. Then we have at the upper end of the link 3, we have an hinge joint attached to the bracket, and the pin joint again attached to the bracket. So this was the joints of the linkage mechanism and the landing gear. Then for the actuation of the wheel assembly, we have given a motor which will be rotating it to an angle of 75 degree via a step dwell function. Here we can define the function as we want. So the motor start time is 1 second and step on time is 5 seconds. So it will reach, 0.5 seconds. It will reach and full actuation with 0.5 seconds. Yeah. So again, then up next we have the actuator, which will be responsible for the linkage lowering and the lifting of the linkage mechanism. So this actuator is of pneumatic type, and it has an overall displacement of 22 mm. Again, we have here defined the function of step tail strap. Firstly, the actuator will be fully actuated within 2 seconds. So this was all the setup of the motion analysis of the landing gear. Then we'll be simulating the motion. I've already simulated the motion here. And these are the or the parameters for the motion. The end time for the full motion analysis is 5 seconds, and we are doing a transit analysis, and the gravity is on. So this is how the landing gear motion analysis. You can see the wheel assembly is properly lifting, and again after an interval of 2 seconds, it is again lower. The motion analysis helps us to identify the forces at the actuator and the motor, and the torque required at the motor. As we can see here, the first actuator has a max force of 80 newtons, and the motor requires an overall torque, a max torque of 60 Newton millimeter. With this motion analysis, we can identify the forces and the displacement at various links, which will be helping in the designing of and improving the landing gear of the human bomber. So, via Inspire, we can simulate and also optimize and analyze various parts in the linkage mechanism. So, Inspire is very powerful tool. So here we have successfully replicated the linkage mechanism and the lowering and the lifting of the landing gear of a B-1 bomber aircraft. And also we have identified the forces required at the actuator and the motor end.